Welcome to Unit 9, Lecture D. Today we're going to review a few things about voltaic versus electrolytic cells and some of their applications. Okay, so to wrap up a few points, EO values or electrode potentials. We no longer have a chart of electrode potentials in our notes, but you may run across these from time to time, especially if you go on in chemistry. So the electrode potentials help us decide what the voltage would be in a battery. So if we take this equation, magnesium, pure magnesium 0, pure chlorine 0, magnesium chloride, magnesium's in group 2, so he's plus 2, each chlorine's minus 1. And we were to write the half reactions. Magnesium's number goes up, so he's the one being oxidized. Oxidation is a loss of electrons, so electrons are on the product side, and to go from 0 to plus 2, you lose 2 electrons, so that our charges are balanced. Chlorine is going from 0 to minus 1, that number is going down, so that's the reduction. Reduction is a gain of electrons, so we are going to gain 2 electrons, 1 electron for each of the chlorine atoms to become chlorine minus 1 ions. If we look at some EO potentials, and I already highlighted on this chart the magnesium. This is magnesium plus 2 electrons becoming pure magnesium. That's the reduction of magnesium because the EOs are standard reduction potentials, so it's negative 2.3. Since that's the reverse of what we have here, we need to use positive 2.3. The chlorine is exactly the way we wrote our equation, so we just use the number the way it is, 1.36, positive 1.36, and to get your total electrode potential, what the voltage would be, just add the two together, and this would be a spontaneous reaction. We don't have that chart, so they can't ask you quantitative questions with numbers. They will ask you more qualitative questions, and you're going to use reference table J to do those. So again, J, most reactive elements to the top. For metals, that means the highest one is oxidized. And for the nonmetals, that means the highest one is reduced. If we look at a multiple choice question, like the one below here, magnesium here is 0. If this were to react, he would have to become positive. And the lithium, which is positive, would have to become 0. So from 0 to plus, the magnesium is being oxidized. From positive to 0, the lithium would be reduced. And that's the same pattern for all of these. If this was spontaneous, the magnesium would be oxidized, the barium reduced. Oxidized, reduced, oxidized, reduced. So if we use table J, and I highlighted the magnesium and the 4 choices, if it's going to react, the magnesium has to be the one that's oxidized, so the magnesium has to be the highest of the pair. So the only one that magnesium is higher is for the silver. So that means this is the only reaction that would react spontaneously. If you have a battery and it has this EO potential and the charge, as the battery uses its electricity and the concentration of your reactants goes down, the charge potential also goes down when a cell reaches equilibrium. And we no longer have this flow of electrons, so in essence your battery is dead. The EO potential is 0. We're going to summarize some information about voltaic versus electrolytic cells. Remember that voltaic cells are the spontaneous ones. They are batteries. And you're always going to have 2 half cells. The electrolytic cells are not spontaneous or non-spontaneous. They are going to need an electron source. And you are going to see only one container. There are electrodes in both. Both have electrodes. One is called the anode, and that's where oxidation happens. The other is called the cathode, that's reduction happens. Anox, red cat, applies to both voltaic and electrolytic cells. The anode is where oxidation happens, reduction happens at the cathode. What's different is their charge. In a voltaic cell, the anode is negative. In an electrolytic cell, it's positive. And then the opposite for the cathodes. In a voltaic cell, the cathode is positive. The electrolytic cell, it's negative. I like to remember this by saying the voltaic cell is spontaneous and cats are positive. That's right. So that's how I remember that the voltaic cell, the cats are positive, and then the electrolytic cell, which isn't natural because it doesn't happen spontaneously, is where they become negative, and I just reverse it in my head. Electroplating is a technique for using your electrolytic cell to coat a metal object, an object with a thin coat of a metal, usually a more expensive metal. You want to attract positive metal ions. So you're going to attach it to the negative electrode. Since it's an electrolytic cell, that means it's the cathode. The other way I remember that it's the cathode is that you want positive ions going to their zero form, so that's reduction, and red cat still applies. So you want to attach your object to the negative cathode to attract positive ions and reduce them to their pure form. That's what they're going to ask you about electroplating. They also might ask you to write the half reactions out, and you should be able to do that by now. In voltaic cells, they might ask you about the electron flow. They're not going to ask you about the electron flow in electrolytic cells because that is not spontaneous. So it's only going to happen in these voltaic cells or in batteries. Electrons flow from A to C, from the anode to the cathode. How do you know which is which? Use table J. The highest of the two metals is the one that's oxidized. So ANOX says that my anode is the one that's oxidized. They're going to go from that species to the cathode, which is being reduced, red cat. Anodes and cathodes, again, use table J, figure out which one's being oxidized. ANOX, red cat, just memorize that and you're good to go. The state likes you to know a couple of specific examples of batteries and how we apply voltaic cells. And specifically this lead acid battery, this is the one that's in our cars. You should realize that you can't just dump a car battery out because they tend to contain really toxic chemicals. So let's just look really quick at what's going on here. So we have pure lead plates, and we have lead oxide plates. That makes this lead plus 4. And it's in a sulfuric acid solution. None of the oxidation states are going to change for the oxygen or for any of the sulfuric acid components, so I'm just going to leave them. They're spectator ions. In the discharge phase, so this is when you're using the battery, the lead turns into this lead plus 2 in the lead sulfate, and we have water, and it produces electricity. We use this in our car. So we use this to start our car when we're running in auxiliary mode. When your engine is running, we do the charge reverse reaction, and that lead plus 2 is going to turn back into lead 4 and lead 0. So for the forward reaction, if you want to know what's oxidized, we have lead 0 turning into lead plus 2 electrons. What's being reduced is this lead plus 4 gaining 2 electrons and becoming lead plus 2. If we're looking at the charge reaction, all we have is lead plus 2. So some of that lead plus 2 is going to turn into lead plus 4 by losing 2 electrons, and some of that lead plus 2 will be reduced by gaining 2 electrons and becoming pure lead. So this reaction they want you to see as an example because it's not really common to see the same species being both oxidized and reduced, but it can happen, and that's how our batteries work. There's alternating plates inside of that battery of lead and lead oxide, and the solution has this lead sulfate in it. So again, don't mess around with a car battery. Don't crack them open. Don't just throw them in the garbage. They need to be recycled because all of this lead is bad for the environment and toxic to you. We see a lot of rechargeable batteries now that are different than the lead ones, and these nickel cadmium batteries are pretty popular right now. Again, discharge is going to be the forward reaction and charge the reverse. The nickel here is going to be +4. The oxygen is a spectator ion. This cadmium is 0. The water are all spectator ions. This nickel is +2. The hydroxides are spectators, and this cadmium is +2. So in the discharge, you have nickel +4 being reduced to nickel +2 by gaining 2 electrons, and you have your cadmium being oxidized into cadmium +2 by losing 2 electrons. Discharge is going to be the opposite. That's just going to be the reverse of these. So in the charged state, your nickel +2 is going to turn into nickel +4 by losing 2 electrons, and your cadmium +2 is going to gain 2 electrons and turn back into cadmium 0. Oxidation is a loss and reduction is a gain. What's reduced in the forward is oxidized in the reverse. What's oxidized in the forward is reduced in the reverse. When you look at a battery and you see the little positive and negatives on the ends of them, those are telling you which one's the anode and which is the cathode. All right, one lecture left for this unit, and we'll be wrapping it up with industrial applications of redox next lecture.